So relatively recently, both Will Prowse and Lithium Solar have had videos where they've talked about the expansion and contraction of the prismatic cells through the charge and discharge cycle and what that might do to the bus bars. Both of them have decided, I imagine because their deployments are static, that they're going to stick with the rigid bus bars. The logic being that there's only two interface points, the post to the bus bar, post to the bus bar, fewer points of resistance, lower heat generation, lower power lost to resistance, converted to heat. This got me wondering though, when a battery is being intended to be deployed on a vehicle, a boat in my case, but it could just as easily be an RV or a van or whatever, when you add the expansion contraction of charge and discharge on top of the natural vibrations and shocks of being on a vehicle, how much does the chance of the connection between the rigid bus bars and the batteries becoming loose over time, either because the vibration has caused the bolts to start to back off, or because the pressures have started to cause the bolt to wear away at the relatively soft copper? This started to worry me quite a bit. The only fire I've ever found when it comes to these prismatic cells seems to have been caused when the junction point between a battery and the bus bar loosened and the resistance jumped enough that the heating got to the point where it was able to ignite the surroundings and start a fire. And I believe it was a cabin that burned down. If I can find that story, I will also link to it in the description. With this in mind, I started thinking, well, maybe flexible bus bars are worth the effort. Not just worth the effort, but actually safer in the long run, even though there's no more points of resistance. My logic is this. When you build a flexible bus bar, you now have 5 interfaces per battery connection instead of 2. Where with a rigid, like I said, you had the 2 posts, and that's it. Now you go post to ring terminal to wire, wire to ring terminal to post. That's 4 junctions. 4 junctions. So the biggest argument against flexible cables, beyond just the pain in the ass to make them and the cost to make them, has been, well, you now have more points of resistance. But because the wire flexes, the energy from the vibrations and the movements in the vessel or in the vehicle, if it causes the 2 cells to move a little bit, that movement is absorbed by the wire moving. It's not transferred onto the posts of the batteries. So my thinking is that though the initial resistance might be somewhat higher, how much higher? That's what we're going to find out in this video. It's going to be more consistent over the deployment life of the battery. In this video, we're going to do 2 tests. One, I'm going to make the 15 jumper cables, and then I'm going to bolt all 15 of them together, and I'm going to measure the resistance at either end. And then I will do the same thing with the bus bars. And I'm going to measure to see, can I see a difference in resistance at all? The second test is going to be to reassemble the battery. First, with the rigid bus bars, as we've done, and I'm going to put it under a relatively high load. We're not here to stress test them, I just want to have a consistent load. And then we're going to use this new toy, an infrared thermal camera, to see what does the bus bar look like when it's under load. Can we see any kind of heat being generated in them? And then I'm going to pull it apart, put the flexible bus bars in, and repeat the test. And again, watch it with the infrared camera, the thermal camera, and see, do we notice any difference in heating? I think we're going to find that there's negligible difference between them. And if that's the case, I'm going to use flexible bus bars, again, to allow for a certain amount of movement between the packs without the movement energy being transferred onto the battery posts. A comment on compression, which was the root of all of this. The argument for compression is that you'll get, instead of 2,500 charge-discharge cycles before you've degraded to 80%, you'll get 3,500. That sounds like a huge difference, and it is. But I'm not worried about that, and here's my reasoning. Battery technology is moving forward at an absolute clip. At 2,500 charge-discharge cycles, I'm already more than 5 years of every single day fully depleting and recharging the batteries, which I'm not going to do. But even if I did, okay, so the batteries last 8 or 10 years instead of 6 or 7 years. Honestly, at the end of 6 or 7 years, if I'm still on the boat, I'm probably going to be looking at these new batteries and their surely improved capacity and say to myself, I want those batteries anyway. I want more runtime. And I'll be looking to replace the batteries anyway. So given all of the hassle of compression, building a rig to do that, I don't see the value in it. I will fix the batteries in place, obviously, to minimize the movement in the vessel, but I'm going to accept they're going to move a little bit. And therefore, again, why I'm really leaning towards the flexible bus bars. Oops, can't see shit. I need to decide how long to make the jumpers. So I'm going to use the black wire. I have no particular reason to use it, except I made a long run of red, so I'm going to use up some black and help balance it out. That seems about right. There. That's how big our jumper is going to be. So one of the tricks whenever you're doing something repeatedly is take one piece as your reference and use this one as your constant reference. Don't like use this as a reference for this, cut this, put this aside and use this as a reference for the next one, because your mistakes start to accumulate over however many pieces you're using, and it really does make a difference at the end. Oh, this is so much nicer than the edge cutters I was using before. 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now, because I'm going to be in the groove, it would be a lot less annoying to have a spare made now. 16 is spare. So I have one extra jumper. Just in case when I go to do this, I find that I have a high resistance on one particular one for some reason, I can throw it out and I've already got a spare. Or I just lose it. Or. I have these. I'm going to need 16 is 32, 31, 32. One down, 31 to go. It's going to be important to keep this alignment and this alignment together so that I'm not putting a twisting force on the wire when I put it on the battery. I think I'm going to have to tie my hair back. One done, 15 more to go. This cabling session interrupted by an adorable little kitty. Want to say hi to YouTube, Tatters? You gonna go off now, buddy? I get my lap back. He's a very adorable kitty. He's very old. I love him lots. And when he wants cuddles, I'm going to give them to him. Let's get back to making cables. Oh, hey, Lynx. You gonna come up and say hi now? I'm ready for my close-up, Ma. So, one thing I've decided, pre-mounting the ring terminal into the crimper, getting just enough pressure on it to hold it in place, and then putting the wire in and pressing it down the rest of the way, definitely the way to go. So now I've got my 16 jumper cables, flexible bus bars. I don't know what to call them. I am now going to test the resistance of each individual one, see if any of them have a bad connection, and if they do, I will recrimp them. Once I'm happy with these, let's bolt them together. First one, clip and clip. Yep, they all measure unmeasurably low resistance. Brilliant. So I have made all the jumper cables and I was figuring out how to link them. The documentation, can you zoom in please, is showing 8 Newton meters of force on the bolt. So I have set, I don't think this is coming across, but it's set to 8 Newton meters currently. So I have a bunch of these bolts. What I'm going to do, did the first one, get it close. That wrench just acts as a backstop. And then, I don't know if you can hear this on my mic, but did you hear that? When the torque wrench gets to the assigned value, it goes click. It kind of like jumps a little bit. And that's how you know you've got the right value. So, I'm going to do that for all of these. And that gives me a set amount of pressure squeezing the jumpers together. That way, when I do the same thing on the bus bars, I'll have the exact same pressure on all of the joints. So the only thing we'll be measuring different, oh, that's the wrong one. The only thing we will be, these are going to be over the place, whatever. The only difference between the two tests is going to be that one's going to be the solid bus bars. Come on. One's going to be the solid bus bars and one's going to be the flexible bus bars. So I'm using the alligator clips because they apply a consistent pressure on the two ends. All of the bolts are torqued together. I have my 15 jumpers, which is going to match the 15 bus bars. And let's see what we have for measurable resistance. And I'll leave it on until the number stabilizes. It seems to be settling in at 0.1 ohm. Now, I get to rip apart my battery. Oh joy, oh bliss. All right, the flexible bus bar has been taken apart. Now it's time to assemble the rigid bus bar. Still set to 8 Newton meters on the torque wrench. One done. 14 more to go. All right, I got my 2 main bus bars. And now I'll join them into a U shape. The idea behind this U shape isn't that it changes the resistance in any way, it just makes it easier for me to touch the two sides. So the settled resistance was 0.1 on the chain of flexible bus bars. And we have 0.2, 0.1. 15 of the jumper cables that I made, strung together, measured 0.1 ohms of resistance. And the 15 rigid bus bars also measure 0.1 ohms of resistance. So resistance without current is one thing. Resistance with current is another. At least I think it is. So I still need to rebuild the battery. This is going to take a lot longer. I need to terminate all of the BMS leads as well. So I'm going to call it a night now. But at least on the raw resistance number, there is no difference between flexible bus bars and rigid bus bars that come with the batteries. If there is a difference, it's to at least 2 places after the decimal place. And I would actually say that this was better because this went to 0.1 ohms almost immediately. The bus bar sat at 0.2 for a bit before it finally dropped down to 0.1. What I'm going to do today is I finally bought the correct size ring terminals. You can't see that. I bought the correct size ring terminals for the balance leads. So whichever bus bar I end up going with, at least now the BMS terminals will be mounted correctly. I brought you down here because I didn't want to take all this up there. These edge cutters are really nice for doing small work like this. However, the tips are very brittle. So it's not uncommon you go to cut with this and the end of the tip goes flying off. So this is actually something you do want to be wearing safety glasses when you use. Get a bit more. 1. And I need 18 of these little pieces. Let's cut them off. $18. There we go. You know what? I think I might want to double this up. So I'm just taking this, coming halfway, folding it back, just to give more purchase inside the barrel. Yeah, that feels better. See, it won't fall off. Pull this up. Voila! I know the lighting's not great, but this will actually fit over the terminal of the battery. As I record this, it's almost October, and outside I can hear the birds singing and the air is nice and cool, and it feels far more like a spring day than it does a fall day. Alright, that's the last one. Now I need to get the heat gun out and shrink all that tubing. So I've pulled the battery out so it's easier to see. Now that all these are terminated, I'm going to put the solid bus bars back first, and that'll be the first thing we put under load and watch the temperature of. Alright, that's 6 Newton meters of force. Okay. There, removable tool sleeve. So these are all torqued now to 6 Newton meters. All right, let's reassemble the battery. So that's the main battery negative. So we're starting here. Three, 4. It's a bit weird. I'm used to having these in the center of the bus bars. Now they have to go on the edge. Now, grabbing the torque wrench, I'm going to do the same 6 Newton meters. There. All back together, all bolts torqued to 6 Newton meters. I'm going to put this back on it now. I'm going to take the BMS leads and we're going to do our voltage check. 50. 53. Okay, so those are right. So soft on the BMS. Pre-charge resistor. 53 volts. Okay, we're good. Okay, so the battery has been reassembled. It's going to take me a bit to get things set up to do the load test, so I'm going to stop here for a little bit. So I'll see you guys in a second. I'm going to go have a break. Slow though I may be, I do learn. Check to see if we have any power. I've turned off the battery, the solar panels. I don't know if you can see. You can't see that. Okay, you have to believe me. 1.1 volt. Okay, so it's off. What I'm going to do, I want to put as much load as I can on the batteries to try to give the best chance of heating. Even then, it's still going to be well below 1C. So be it. So I'm going to move the second breaker off of line 2 over to line 1 so that I can pull 40 amp at 120 volts AC. I'm not going to be able to pull 40 amps, but I want to put my, you'll see this in a second, I want to put my stove and my hot plate to 100% for say 5 minutes. That should give me a pretty good idea of what kind of heating I'm going to get out of the battery. Good enough for the relatively short period of time this is going to be configured this way. Pre-charge resistor, 1, 2, 3, 4, 5. Contact. So this is a giant pot of water. I don't expect to be able to boil it. Like I said, I'm going to do about 5 minutes per test. I'll use my phone as a 5-minute counter. Both AC breakers are on. Time to turn on the inverter. Whoop. Okay, well, clearly that's working. There we go. Oh, interesting. Can you see this? This bus bar seems a little bit warm, as does this one. I mean, not much. You can see what a difference my finger made. Let me double check the torque on these. Set, set, set. Yeah, they all feel set. Where's the timer? I'm setting a 5-minute timer. That's the starting position. It still shows one bus bar as being warmer. Why? Not sure why that's showing warmer, but it's not warmer by much. Okay, let's get going. 550 degrees, set this to on, come up here, set the power. All right, here we go. It's neat, looking at the thermal camera, I can see the BMS warming up. I can see one post warming up. We're currently pulling, I'm trying to get not too close to this, 53 amps, 2780 watts out of the battery. We're sitting at the highest measured temperature right now, being 25 degrees Celsius. No appreciable warming. There's no appreciable warming. Words. You know what? I'm going to boost this. 5:30 start. Okay, well, it's not going to be the most scientific measurement because I hit the wrong thing. Anyways, oh, there's the +1 minute. So it'll be about 10 minutes all in, and then I'll let everything cool down. 2,800 watts, 53 amps. Oh, I should mention, during this test, the solar panels are off. You can see there's 0 watts coming in from the PV. Still pulling 53.8 amps. 3 minutes left. BMS is getting a bit toasty, but the bus bars are totally chill and cool. This is making me realize just how useful of a tool this infrared camera is going to be down the road, to be able to identify if any of the connections are not good. You're gonna have to buy one of these, Andy. Oh, that's neat. You can see the line going back to the positive post starting to warm up. This thing is so cool. Okay, so that wire is warming up more than any of the bus bars. If that wire gets hotter than the flexible bus bars, I'm going to consider this a success, because we'll have a thermal problem with that long wire before we would with any of the short jumpers. But anyways, I shouldn't prejudice the results. 30 seconds remaining. And we're still drawing 2,800 watts, which is 53.6, 53.8. Let's just call it 54. We'll round up to a nice even number. And there we go. Test over. So to put this into context, this is showing us the warmest part. And well, you can see the heat of my hand is hot enough that you can actually see the imprint on the cable. So yeah, it's the hottest thing here, but the BMS is by far the hottest piece. This camera is so cool. Holy crap. How's this look? I gotta look at everything now. Okay, that was the test of the solid bus bars. I'm going to let everything cool off, and then I'm going to swap them out for the flexible bus bars, and we'll repeat the test. Let's switch out to flexible bus bars. You know what? If I made these again, I'd make them shorter. They are long enough to be able to touch multiple posts at the same time. I don't like that. However, gotta start somewhere. Yeah, the springiness of these wires is pushing the batteries apart, but I'm not too concerned about that because the final box will fix them in place. Not compress them, fix them. Everything is torqued down to 6 Newton meters. Let's set up for another test. The oven is cool. The water has a surprising amount of heat still in it. Okay, oh yeah, I gotta set the thermal camera. The hottest part so far is where I was sitting. Wait, am I actually ready? Yeah. 1, 2, 3, 4, 5. Contact. I wonder if the smart shunt loses its history when the power is pulled, because it's saying it's 100% battery now, and it's very much not 100% battery right now. Huh, a mystery. Okay, the FLIR has started recording. Everything's ready. Let's do this. $550, turning this on. Set power to 4. And starting the timer. Here we go. So it's showing really pink, but that's just because the current max temperature is 25 degrees. Currently drawing the 2,800 watts before, 54 amps, minus a little bit. One of the things I just noticed is that If you recall, when I was first setting up to run the test with the rigid bus bars, I saw a couple hot spots. I don't see any specific hot spots with the flexible conductors. Light on one side, lots of shadow. Very gloomy. I was going to be happy if the flexible bus bars were about as good as the solid bus bars. I'm starting to think they might actually be better. Talking above my nose line. Hello. Enjoy a little grown-up apple juice while we wait. I like my whiskey chilled. 6 minutes to go. Still pulling 2800 watts, 53.6 amps. No visible heating at all from the flexible bus bars. The long wire is warming up, but all of the actual jumpers are perfectly cool. Better than the rigid bus bars. The fact that I'm seeing the long run start to warm up and nothing on these flexible bus bars. Yeah, I think this is a winner. I really think this is a winner. Okay, Kitty, this is really not a kitty-friendly zone. Absolutely nothing on the bus bars. It's better than the rigid. Wow. I was not expecting that. I thought it would get at least a little bit warmer than the rigid. Hey, Lynx. We're doing science. Inductive cooktops are amazing. It's already steaming. Cooking with magnets and batteries. 2800 watts, 54 amps. A cat in the thermal camera? Absolutely nothing. Absolutely nothing on the flexible bus bars. So as far as I'm concerned, this settles it. Flexible bus bars are better than rigid. If only because, as you saw with the rigid bus bars, there was a couple of hot spots. I'm assuming because the metal plate wasn't sitting properly on the top of the bus terminal, generating a little bit of heat. With the flexible bus bars, I'm able to wrench it down, and that's going to sit the ring terminal right over top and make a good connection with the top of the battery terminal. That's all I can think of. If you have another theory, please post it below. I have relatively limited capabilities to do testing here. This is not supposed to be a testing channel. That I very much leave to people like Andy and Will Prowse. Because of this, my battery is designed for a maximum draw of 100 amps. It's limited by the BMS, in fact. I would love to see this test done by somebody like Will Prowse or anybody else. If anybody out there happens to be able to talk to any other YouTubers who are doing battery builds, who have a capability of pulling, say 1C, 280 amps, if they could repeat this test using flexible bus bars versus rigid bus bars and see if instead of at 54 amps, 280 amps, can you see a difference? Prove me wrong, and I'm not saying that in any kind of a sarcastic way. Literally, please, test this and see if you can prove me wrong. I would love to know how well this scales. Again, to restate, these are 4-gauge anchor wire, so marine grade wire, with TE Connect 1/4 inch to 4-gauge ring terminals. If anybody wants to repeat this test and you're curious about anything I've done here, send me a message. I'll tell you exactly all of the components I used, my test parameters, everything, though I believe it's going to be in the video anyway. The reason I'm sort of shocked right now is that I'm surprised nobody else has built flexible bus bars. Now, to be fair, it was a pain in the ass to make all of these flexible bus bars. And for static installations, it doesn't make a lot of sense because once you fix the battery in place, it's not moving. So if you're in a cabin or whatever, Lynx, you're making me very nervous back there. You know what? I'm gonna put the cover back on the battery right away. Is it better enough that if you have a static install, like in a house or a camp or something like that, where there's minimal vibrations and minimal movement, do I think you should go and replace your rigid bus bars with flexible? No, absolutely not. I don't think the difference is that big. However, if you're installing the battery into a vehicle, a boat, an RV, or anything else that moves, then the fact that the flexible bus bar, by its very nature, has some give to it, means that the packs, if they do receive some energy, can slide back and forth, and they don't transfer that torque onto the terminals. I keep repeating myself because I was not expecting this result. I'm still trying to process it. These are definitely better. I'm going to say that. Anyways, science with the Digital Mermaid. See you next time.